Alright, welcome to the 9th video in our forces unit where we're going to talk about friction, something we've talked about many different times. Now we're just going to get a real concrete idea of how to deal with it in problems, how to put it on free body diagrams, and how to manipulate the equation so that we can work with it. So the question is, why is it hard to drive on ice? Well, tires and road, there's a certain amount of friction. When we're driving on ice, that changes. Normally, if we're driving, friction slows us down, we come to a stop, and we're all happy. On ice, we'll either keep going because we just can't slow down fast enough, or the wheels lock up and we start to skid, and then we have a lot less control and we can end up flipping over, and that's just not a good thing to do when you're driving. So friction has a lot of more purposes than just driving. Without friction, our world would be entirely different. You wouldn't even be able to use a pencil. So just think about all the different ways that friction matters in your life. But we're going to actually only study two of those types of friction: static friction and kinetic friction. Just as the words would imply, static friction has to deal with when an object is at rest and it wants to stay there. So it resists the change from staying at rest because it wants to stay there, but you're trying to change it. It resists that. Kinetic friction, on the other hand, is when an object is moving, and so there's a different value of kinetic friction when something is moving. So what we're going to look at is just a little bit of an example of that. So if this block here is at rest and I try and push on it, it doesn't move, and that's just because I'm not applying enough friction to overcome static friction. Static friction, when I'm not touching on it, is 0 because it doesn't have to do anything. It's only when I try and change it from being at rest will static friction resist that change. It will go up to a maximum value, and when I overcome that maximum value, it will start to move. Once it is moving, we now don't have static friction, we now have kinetic friction. So there's a key difference there, and when we get to the equations a little bit later, we'll also see that one is always greater than the other. So, in terms of things that we won't talk about, rolling friction, when balls are rolling, tires are rolling, we're not going to talk about that. And fluid friction, where that's a lot of air resistance and water flowing through pipes, it gets a little bit too math heavy, and it's just you don't have that background to be able to solve it until later in the university. So we need to deal with the frictions we can deal with and how to put them on our free body diagrams, static versus kinetic. So we've got the two situations. We've got an object in motion or an object at rest. How do we know what direction friction acts? An object in motion is the easier one, so we'll start there. So if this block is in motion, I have to keep pushing on it in that direction that I want it to go, because friction opposes the direction that it is traveling. So if I'm pushing on it that way, the friction is going to go that way. So we've got force applied, force of friction that way. If this object is at rest, is a little bit different situation. If it is at rest, I'm going to apply the force to it, doesn't move, because I'm not strong enough, I'm not pushing it hard enough. So it's staying there, but I'm applying a force to it. Static friction must act on it. If I'm applying a direction that way, static friction is still going to be that way. But it's because if there was no friction, the object would go this way, it would travel, but because there is friction, it's not. So it's still opposing the direction the object would travel. Slight difference that makes a difference when we're talking about why things stay there while we're going on it, because it is moving in a certain direction, but there's friction keeping that one from moving relative to the top. So it can change that situation, and we'll look at that in class. So that's exactly what we have written here. So we've got that an object in motion, the friction is opposite the direction of that motion, and if that object is at rest, it is opposite the direction the object would go if there was no friction. So what we want to talk about now, though, is what affects friction. So there are a few different things, but what we're going to look at is we've got this block here on 4 different surfaces, and we're going to think about how much force it takes to slide it across this surface which is like a rubbery surface, compared to this cork, compared to the sandpaper, and this smooth wood at the end. The surface clearly makes a big difference. If I'm thinking about trying to rub wood over sandpaper, it's a lot harder than rubbing smooth wood on smooth wood. As is, cork is even easier than the sandpaper, and the rubber is easier than the cork. So they're different depending on the surfaces. And the other thing is, if I'm pushing down on this, say I'm pushing it down on the sandpaper, it is much harder to try and get it to move, as compared to just having it lightly put on there. I can move it this way. But if I'm trying to push down on it, it makes a difference. So that's just like if I put this car in here, it is now harder to move because there's more force pushing the two together. But that might not be all of what makes a difference. So we see here that the surfaces in contact make a difference. The amount of force pushing the surfaces together makes a difference. But the question is, what else, if there is anything else, that makes a difference for friction? And we'll talk about that in class. Now let's get to some formulas. So we have kinetic friction, which is fairly simple. While static friction is almost going to be exactly the same, but we've got F of force of friction, so FF, K, lots of subscripts, is equal to mu K F N. Now this is mu is a Greek letter, and we use that for a very important thing, which mu K is the coefficient of, not static, of kinetic friction. And so that's a value that is unique to each type of material, and Fn is our normal force. So that's how we can calculate the force of kinetic friction. If we know the normal force and we know the coefficient, we can figure out the kinetic friction. Now let's think about a situation. If we're thinking about Newton's first law, we've got a block being pulled along the surface at a constant velocity. If we're doing that, we need to think about why the frictional force would be equal and opposite to the direction that I'm pulling. So let's draw a free body diagram. We've got an applied force, we've got force of friction kinetic, Fg going down, and Fn going up. What we're going to look at though is only the horizontal direction in to get what we need. And so we get F net equals 0, and that would be Fa plus FFK. With our vectors 0 newtons, we can take off our vectors, so that'd be Fa minus FFK equals 0, which tells us that Fa must equal the force of friction kinetic, which is exactly what we should expect. Now let's look at static friction, which is a slightly different formula, only minor. We get FFS is greater than or less than mu S Fn. So very similar, but in this case we have mu S, and this is the coefficient of static friction. Fn is the same, normal force, but the big difference here is the less than or equal to. And what that means is that the static friction can go from 0 to a maximum value. In problems, we're always going to probably be looking for that maximum value. How much force can we apply before it moves? So in problems, it'll almost always be Fs is equal to. You don't worry about the less than. But it can be from 0 to that maximum value. And it again depends on the normal force and mu S. Now this one is always, so at the maximum value, it is always more than FFK, which is interesting. So it actually is harder to get something moving than it is to keep it moving. which, if you've ever tried to push something very heavy, is actually very true in reality. Now, these friction forces are vectors, but we actually will never have vector quantities in these formulas. That's why they're not written with vector arrows, because they are perpendicular. When things are perpendicular, the directions aren't what we're using. All we're using is the magnitudes of these values, and we apply the direction in our FNet equation. So FF and is always going to be kind of just a magnitude, or you can think of it as a scalar. What I want you to do also for next class is think about some situations where we would want a high coefficient of friction and others where we would want a low coefficient of friction. That'll help us think about what a coefficient of friction is, and we'll see you in class with lots of these ideas. Physics is awesome.